A very good afternoon to all of you. So this is in continuation with the online course Hydrometeorological Hazards. So this is the third lecture in this series, and today we are going to talk about hydrodynamic modeling and advances in geospatial data and its application, how this hydrodynamic modeling can be used for different applications. So that we'll try to see in this today's lecture. So myself Pankaj Ardhote, and I am working as scientist SE at Water Resource Department of IIRS. So this is the brief outline that we are going to talk about in this lecture, that what is hydrodynamic modeling, then application of hydrodynamic modeling, input data required and challenges, and then we'll go through the different case studies where this HD modeling can be used for different applications. So that we'll try to go on a one by one basis. So here you comes to the first we'll talk about the what is hydrodynamic modeling. So now if you look if you look into this particular figure, here you can see that. So this is the green one that you are saying. Suppose at this particular the first point I have certain information, like suppose at this particular point I have information of hydrograph, right? Now it could be the water level also. Now I have the information at this upstream end, and I want to know the certain information at the downstream end, like so all these red points that you are seeing. So suppose these are the points where I don't have the information of discharge and the water level or the corresponding like velocity, the flood extent, all those things I don't have the information about those at the downstream end. Now by knowing the certain information at the upstream end and we try to find out the information at the downstream, this is, if you go back to the hydrological basis, we know that is we call as the flood routing. So now this hydrodynamic modeling comes under the one of the method of flood routing. So one of the method is that what I was saying is basically the Saint-Venant equation. So this equation that which is one of the method that is being used to route the flood wave that is there in the upstream, and we try to see what is the impact of that flood wave on the downstream side. So now the Saint-Venant equation, this is the 1D form of Saint-Venant equation, which includes the continuity equation and the momentum equation. Now we try to give solution to this these two equation by using different numerical scheme. Now this is what we call as the hydrodynamic modeling. I will just read out the process of providing numerical solutions to the river flow governing equation. Now in this case the river flow governing equation are the pair of Saint-Venant equation, and then we try to quantify its dynamics in terms of water level, velocity and discharge at the downstream, and that is what I was saying. I have the certain information at the upstream, and I try to find out the discharge and then water level at the downstream end using this Saint-Venant equation. This is nothing but the we call as the hydrodynamic modeling. Now to give the solution to this partial differential equations, we have different modeling packages, like you have this open source HECRAS, and then you have this commercial softwares like MyQLM and TubeFlow. So all these the packages provides different pre-processors and the post-processors. Based on that, they work differently. They have the little bit difference will be there. You will find in the outputs also. But all this the software packages that are there are the basis of or they use the same equation, the same Saint-Venant equation, but how they give solution to this equation, like this partial differential we convert into the algebraic, and then we create a matrices, and then we try to find out these different variables. In this case the variable is the H, that is the water level, and then Q you can call it discharge. So these are the two variables that we are interested in at all the different river reaches at the downstream. So at the end the output is same, that is what we look for, and the equation is same, but the approach, the way they solve, that is where this modeling packages vary. Now I was saying, so after setting up a hydrodynamic model, the same model can be used for different approaches. Like you can use this model for flood inundation mapping of historical and future extreme events. So you take a hydrodynamic model and you run that model for a historical time series, and then you can generate the different inundation maps, flood hazard zonation of different return period discharge magnitudes. Again, you run the same model for, suppose you run this model for 50-year return period, 100-year return period, 200-year return period, and you try to see that at the downstream area from which you are routing your particular river stretch and what is the impact. So basically, by running same model for a different return periods, you can generate the flood hazard maps. So that is also the one of the application of hydrodynamic modeling. Then you have the flood risk assessment. If you combine your flood hazard with the vulnerability corresponding to the different exposures, the combination of this hazard, vulnerability and the exposure will give you to the flood risk. So we'll try to see one of the case study that we have done on the flood risk assessment also. Then river embankment overtopping analysis. If you know that the now river embankment analysis means, suppose you know this, there is particular river, say for example I talk about the Brahmaputra river or Ganges river, where there is every year there is a corresponding breaching will be there in the banks. Now if you want to identify the structural measures where you can increase the embankment so that overtopping can be reduced during the monsoon season, so that kind of analysis also can be done. You can run the model for extreme events and you find out the different river stretches of a complete stretch where there is the frequency of overtopping is high, and there you can suggest, or you can suggest for overtopping or increasing the level of the embankment so that overtopping can be reduced. So that is also the one of the application that you can be done using the hydrodynamic modeling. Then you have this dam break analysis, glacial lake outburst floods, then landside dam lake outburst floods. So this the approach for all this the latter three applications you can consider into the one category. So you have a sudden release from either from a reservoir when dam gets broke, or the gates of that dam gets released, to heavy flood wave will come from that dam. Or if you have the glacial lake, if there is sudden burst in the glacial lake, so what will be the impact on the downstream side? Or if you have this there is a landslide is there and it blocked your river, and then because of which there is ponding and then creation of the lake, and if that lake gets burst, so what will be the impact on the downstream? So all this kind of different applications you can do it using this hydrodynamic modeling. Now just to understand what are the different input parameters that we require to set up a hydrodynamic model, that we'll try to understand using this particular case study that we have done it for a Tirthan river basin. Now if you look into this, this is the Himachal Pradesh, and then Himachal Pradesh you have this Bias river basin. Now this is the small one, this watershed that you are seeing is the Tirthan river. So Tirthan river is a tributary of a Bias river basin. Now it has the catchment area of 680 square kilometers. So now here objective is to generate the flood extent map for different year extreme discharge magnitudes of 100-year, 200 and 500-year return periods. So that is what we'll try to even though our objective is this, but through this process we are trying to understand that to set up a hydrodynamic model, what are the different input parameters are required. Now on the right hand side that you are seeing, so this blue line is basically the Tirthan river, which is up around 9 kilometers. So I set up this model only for a very small stretch, and that is of 9 kilometers. Now this is the DM that you are saying is of allospersal radiometrically terrain corrected product. So this is the elevation range, how you can see how it is varying right from valleys, and if you go towards the ridges, there is the corresponding increase in the elevation values. Now the first, so now in this case, so we'll try to understand when you set up a hydrodynamic model, how you can generate the one by one the input parameters that is required to set up the HD model. The first one that we are going to see is the river network. Now here you can see, as I said, I'm looking for the river network that is of 9 kilometers. So this is the from here, right from this is the Dari. So Dari is one of the village that is there along the Tirthan river, right from Dari to Larji. So this is the river where I'm looking for. It is stretched around 9 kilometer, and then you have the small rain-fed tributaries. So if you have this data of this rain-fed tributaries also, that you can consider. If you don't have, then you have to go for some approaches, and then by using the data at the from Largi or some different approaches, and then you have to give this you have to consider this rainfed streams also, if the contribution of the streams was very high in case of in this main river. Now the first thing that comes to is how can I generate this river network. Now there are multiple approach considering the nowadays the tools that are available. The first and the foremost method that which you can use to river network is you consider any GIS software, like you have this QGIS, or if you have this ArcGIS, you add there one of the satellite image, you download satellite image. Maybe you can download from Indian satellites. You have LIS4, LIS3, or other satellites like Landsat, Sentinel-2. So these are the satellite images that you can add, or sometimes you will have the base layers in the GIS softwares. So that image, that base layers also you can use, and using that high resolution image, you can delineate this particular river. So this you can delineate. Now once you delineate, you can save this river network in shape file, and then the shape file you can import in any software. Now this interface that you are seeing is basically of Mike 11 software, but same thing or same approach you can follow if in the open source software like IIRS also, where you can set up a hydrodynamic where you can set up a river network where you need to define this using any GIS help of GIS software. This is the first approach where you take help of satellite image. You add that image into the software, GIS software, and you try to digitize the river network. The other way could be you just simply go to the Google Earth, you digitize your river network, and you will get that in the KML file, and that KML file can be again further imported into into this HECRAS or Mike 11, and then you can use to generate these river network. Now this is the first step that is required for generation of the river network. Now second is the cross sections, how you can generate the cross section. So I would say this cross section is one of the most important parameter of hydrodynamic model, because it governs the complete geometry of your channel and your floodplain. So if your geometry is not correct, then there will be your conveyance will be compromised. So how much amount of the capacity of that channel is there to allow the water to flow, so that also will be compromised, and then there will be corresponding uncertainty will be there in the routing, and then corresponding uncertainty the outputs that you get, flood extent, flood depth. So you have to ensure that the cross section that you delineate it is very important. Now how do you generate this cross section? These cross sections you can generate using freely available DMs. Here I have shown this ALOS Pulsar RDC product, so that which has the spatial resolution of 12.5. You can use other DMs based on the which one is your area. If you are dealing with very small area, you should have very high resolution, but if you have very big area, then sometimes it will be very difficult to have DM based UAV based high resolution DM. Then maybe you can go for the freely available DMs, like I have shown here ALOS Pulsar, and then you can go for SRTM, you can go for Aster, you can go for Copernicus DM, you can go for hydrologically terrain corrected, like this Merit DM is also there. So there are number of freely available DM products are there, so that you can use and you can try to extract the cross sections. So this interface that you are saying is basically the interface of Mike Hydro, where you just add your this river network that we have generated, and you add your DM using which you want to extract the channel and the floodplain geometry. You feed those, then you follow certain steps, you can what you can see, you can generate the cross sections like this, right from your upstream to the downstream. So now this is the second step where you can generate the cross sections. Now, as I said, this cross section you are generated from the DM. You did not go actually into the field, so there are certain limitations. Limitations are linked with the DM when you actually try to extract the geometry of channel and floodplain. So if you look into this, this is how the when you download the any satellite DM from the geo portals that are available. So basically the elevation values that you get are basically this. These are the elevation values of this surface. So when you download the DM, so you get these so if you have too much of settlement, then the elevation values that you are looking into it are basically the elevation values of this over this settlement, or if you have trees, or if you have the cars, or anything, any functional class that you have, the elevation values will be very corresponding to. But what we are interested in is basically we need the elevation values corresponding to the bare earth. So that is what should go as an input to your model. So then that is why you have to ensure that this problem will not be a problem when there is no settlement or something like that. But if there is, if you are looking for a densely populated area, then especially if you are going for urban flooding, not just the rural area riverine flooding, but if you are only focused on the urban flooding, then you have to really be peculiar about to considering these uncertainties. You have to go back to the DM, you have to edit, and you have to ensure that you are dealing with this the elevation values corresponding to the bare earth model. So this is one of the challenge when you use DM using the satellite based DM. So this is one of the challenge, and then how we can address that we'll try to also see in the coming slide. So this is what I was saying, that if you have this, maybe you can go for spatial averaging, and then you can try to remove those elevation values, and you can try to approximate the elevation values of the bare earth model. Now the next one is the river floodplain survey. So basically, so the first challenge that I already told you is like basically you get the values of the corresponding to the classes that you have, maybe settlement, vegetation. But what we are interested into the bare earth elevation values. And second one is the when you use the satellite based DM, that those DMs cannot penetrate to the earth surface. So that is why so for floodplain it's perfectly fine, but when you are talking about the channel, so you basically get the elevation value of the water surface. You are not looking into the water depth, so basically you are not looking into the bathymetry. So in that case, maybe you have to go to the field and you have to perform certain survey so that you can actually know the what is the depth that is there in that channel. So then later on further you go to the field, take that data, and then you use that data set to edit the geometry that you have generated using the DM. So maybe somehow you have to go with the hybrid cross section. So this is what one of the GPS, or you can say this GNSS receiver. So now it gives you the exact latitude, longitude, and the elevation values, and it helps you to evaluate the accuracy of the DM that you are using, and also to edit the cross sections that being extracted using that particular DM. Now if you look into this, so this is the this is the differential global position system. So if you combine one is the rover and another is the base, if you consider two different components, and then you try to collect as a number of ground control points. So this one is the DGPS, by which we try to collect number of ground control points. Now this is the total station, so to get the exact river profiling of that cross section. So this is one of the survey that we carried out in the Bias River Basin. So here you can see that, so it was very lean period, so we could go to the channel, and by using this different readings, we are able to find out what is the actual bathymetry of that particular river. So that's why so it help us to evaluate the cross sections that we get from the DM, and then edit those geometry accordingly. So we took certain feeding of different locations. We took from this, some in the channel, some in the floodplains. So now this is typical cross section that I'm showing you here. So this is the cross section that we generated using this total station and the DGPS. So this is here you can see that this so this is exactly what the bathymetry may look like. But if you are using a DM, maybe you will find that you will get a straight line somewhere here. So now there is corresponding drop, or corresponding this depth will not be considered in the DM. So, but if you have this certain surveyed cross sections, it's then this cross sections will help you to edit those cross section that we generated using the DM. Now, so now this we talked about the cross section. Now further we'll move towards the boundary condition. So what this boundary condition is basically, so as name it suggests, so some condition that we give it to the boundary of your particular river network that you are dealing. So now again, if I go back to my river network, so here you can see that, so I have a 4 boundaries, right? So this is my upstream boundary, this is my downstream boundary, and these are the 2 river what you can say, these 2 tributaries. Again, these are the open ends, so those also are the boundary. So I have to give certain information, though that equation will be closed, and accordingly that we can give solution to that equation. So now again, so at each end you have to give the boundary condition. So now suppose this upstream end is there. Now I will give boundary condition, means what, either I will give the discharge or the water level of which I want to see impact on the downstream side, or I want to route that flood wave in the downstream side, right? So suppose I have this data or the hydrograph at this upstream end, so I will give this information at the upstream end. So in this case, what we have done, that I will try to explain. So we ran this model in 2 cases. So if you go back to your objective, so our objective was to run this model for extreme events of 100-year, 200-year and 500-year return period, right? But before that, we want to ensure that this model is working fine. So what we'll do is we'll run this model for some historical events, and then we'll try to evaluate whether this model is working fine or not by doing some comparison between the simulated and the observed discharge. So for that, we ran this model in the 2 steps. So first step is we use some historical data, we ran this model, and then we perform the calibration and validation of the model. So what calibration and validation, that I will try to understand in the coming slides. And then after I ensure that for historical data set my model is working fine, then I use second step my boundary conditions, that is I use this flood frequency analysis, and I run that model for 100-year, then 200 and the 500-year return period. So this is what I have explained here. So this is the Dari, that is my upstream rate. This is open inflow, so I have given discharge as the input. Then output, this is the last downstream and largely. Here you can give this rating curve as your boundary condition, and then rainfall stream. So this is the point source that I given to the river network. So now in this case, this here also you can give your discharge if you have the discharge, or you can give the water level as the boundary condition to this two rainfed streams also. Now next comes is the hydrodynamic parameter. This is the fourth component that is going that goes into your hydrodynamic model. So now what it does is basically, as you know, like whenever there is a flood wave is moving or going from upstream to downstream, it will go through its different classes. Like it will go through your channel, it will go through your some settlement, it will go to the agriculture, it will go to the forest. So each the classes that or land use land core that is there, it will provide different resistance to your flood wave. So accordingly there will be change in the velocity, there will be change in the depth, right? So to account for this, the resistance provided by the different classes, so we have to give the spatially different distributed Manning's roughness coefficient. So if you know this Manning's roughness coefficient or the Manning's equation, where there's n is corresponds to the, or it is used to define the roughness of different classes. So that is why, so it is also the one of the main component of hydrodynamic modeling, because if there is no good match between your observed and simulated discharge at the downstream end, then you try to tune or you try to change this Manning's roughness coefficient. Now, so ideally you should have this land use land cover, and then using for corresponding class you give the different Mannings here. But if you look into this, this is the typical land use land cover that I have, and this my stretch is of around 9 kilometer. Now this my 9 kilometer stretch is falling into this only one class, so this cropland. So but it is not true, because this is only 9 kilometer stretch. If I go to the field, you will find that very small settlements here and here, and somewhere very small patches. But it is the land use product that I have used of very coarse resolution. So it will not serve me a purpose to define the Manning's roughness coefficient. In that case, what you have to do is you have to use some high resolution images, or you can use Google Earth, and then along your this river, this is your 9 kilometer river, you find on the left hand side and the right hand side which class is there, and that according to that class you have to give the Manning's roughness coefficient. So this is very important, how you cross section that you give, and then once it is done, then you can move ahead to the next step. So these are the some literature based Manning's roughness values based on the what kind of channel is there, even if it is channel, what kind of channel is there. So there are certain ranges there that is being so this is one of the tabular images I have shown, but you will get number of references, number of papers where you will have the range that what should be the Manning's n value for your channel, for agriculture, or for the settlement area. It is always better before setting up a model, that if you are working on a Mahanadi river basin, you should refer some previous papers, what Manning's n they have used, what is there in the literature. So that will help you a lot while improving the reliability of your model. Now this here comes to the calibration stage. What I have done is the as I said, my model was set from Dari to Largi. At Dari, that is at the upstream end, I gave this 2005 monsoon season discharge data as input, and then after that I ran this model and generated a certain time series at the downstream end, that is at the Largi. So this is what I have got at the downstream end, that is at the Largi. So this is the, here you can see that the observed and the simulated depth. So I perform the number of trial and errors, and I try to change the Manning's n value till there is a good match between the observed and simulated. So here you can see this is the time series plot, and here you can see the scattered plot. So there is relatively good match between these two. So there are certain statistical parameters also which help you to understand that how efficient your this efficient match is there between your simulated and object. Like you can go for correlation coefficient R square. If it is normally more than 0.7 or 0.75, you can say that your model is working fine. And then if you have this root mean square error, if it is less than the 1 meter, maybe 40 centimeter, 50 centimeter, again then you can say that your model is working fine. Now this is the calibration step, where what you do is, till there is a good match between your observed and the simulated, you try to keep on changing the value of n. You keep on changing the value of n till there is a good match. Now once you are sure that for this values of n corresponding to your channel and n corresponding to the different classes that are there in the floodplain, so these are the different n values. You sure that these values are fixed, and for which set that your this good agreement is there, then you can stop this calibration process, and you can generate the statistics. Now further you can validate your model. Again you run this model for a different year. Maybe you run for, here in this case we ran for 2014, 2014 or 2010, I have to see. So again for a different forcing we ran, and in that time we do not change the n value. So without changing the n value for different time period, maybe 2010, 2014 or any different time series in the future, for that time series also, if your model is giving good correlation value, good RMSE value, then you can say that your model is well calibrated, and then you can rely on this model for further flood inundation mapping or flood hazard assessment. So this we ran model again for 2014 during this what you can say this I have shown you only here for this calibration time period, but I think we performed this for the validation. So our model was working fine. I will share the link of this paper, so you can refer more for this about this particular paper. So for 2014, so this we run this model, and this is one of the output, that how your water level is changing during the monsoon season. That also can be done. Same result I have shown it in the Mycelium, but same this longitudinal profile elevation you can generate in the HECRAS as well. Now this is what, once you are done with your calibration and the validation, you can generate this different inundation map. So like this is for a 500-year return period discharge output. This is the Balichoki village, which is the most flood prone area between the Dari and the large river stage. Here you can see that this is the particular area which got inundated, and then out of if you can see, this is how the your river is meandering, and then this is the particular section. Here you can see that your water depth exactly is going into your area or the village. So this area we identified out of complete village, which one is more hazardous or the flood prone, you can say. Then after identifying this, you for this particular 500-year return period, what is the extent, then what is the depth. So here you can see that the depth is around 4.2 to 4.8 meter. So that kind of futuristic simulations you can do it using this hydrodynamic model. Same goes for if you run this model for 100-year return period or 200-year return period. For 500 return period, it was around 4.2 to 4.8. Then as discharge is reduced, so there is corresponding decrease in the water depth value. So such kind of analysis you can do it for the to identify the which area of your area is more hazardous. Now again, if you look into this, here you can see the output that I am showing you are kind of pixelated, so kind of grid pattern you are seeing. Why I am seeing such kind of result is because the DM that I have used the DM of 12.5 meter for a very small river of 9 kilometer. But if you would have been the DM of very high resolution, maybe 2 meter at least or 4 meter, then more improved result you may get. So now this is till now if you at this till slide we learned about that what are the different steps that you can follow when you set up a hydrodynamic model. Like you generate the river network, and then you generate river network, you generate the cross section, then you give the hydrodynamic parameters to it, and then you run that model for two set of boundary condition, one for historical time period during calibration validation. And then second boundary condition, which was your objective, you wanted to run for your 100-year or 200, 500-year period. So after done this, so this is one of the, through this complete case study, we try to understand that how this hydrodynamic model is generated, what are the challenges in the input data set, and you can how outputs can be generated. Now next we are going to talk about the different case studies that we have done number of case studies. So I have tried to combine the different case studies of which will try to give you the glimpse of how this same hydrodynamic model can be used for the different approaches. Now this first one is the flood risk assessment. Now this we performed in the Bias River Basin. Mostly we targeted for the three main cities, Manali, Kulu and the Bhuntar. So what we did is we developed the hydrodynamic model right from your Manali to Bhuntar, and then we try to do this flood risk assessment. Now as I said, flood risk assessment is combination of vulnerability, exposure and this hazard. Now if you look into this flood hazard rating, so this is one of the hazard rating that the equation is depth into velocity plus 0.5 plus df is the debris factor. So this is the one of the equation that is used for flood hazard rating generation. Now out of this, the depth and velocity are basically the outputs of your hydrodynamic model. You run this model maybe, so this is this complete assessment we did it for 100-year return period discharge magnitudes. After again same thing, we calibrated model, we validated model, and then for 100-year return period we found out what is the depth, we found out what is the velocity, and then we generated this flood hazard rating. So this is how you can generate the flood hazard maps also using the hydrodynamic modeling. Now you can combine this with your vulnerability corresponding to the exposure, and then you can come up with the flood risk. Now this vulnerability, so this flood vulnerability you can generate using the depth damage functions. Now again this depth also again comes from your hydrodynamic model. If you know the you get the depth map which is spatially distributed for right from Manali to the Bhuntar, and now for each depth, based on the what is the depth, there is corresponding value of damage. So so normally for each region wise we will have this depth damage function. For at present we do not have very dedicated depth damage functions for the Himachal Pradesh, so we use the depth damage functions from this GRC report, which gives you the depth damage function for different exposure, like if you're targeting settlement, or if you're targeting road, or if you're targeting the agriculture. So that's how based on that you can generate the flood risk assessment or flood risk map. Now further you can give this flood risk, you can generate this flood risk also. You delineate your complete boundary of your cities, and out of whole cities how much area was inundated, and then you can based on that you can identify the severity, how whether it is high, low, and the warning, low, moderate, significant or extreme. So like that studies you can do it using this using the hydrodynamic modeling output. The next one is the integration of hydrodynamic modeling and the satellite altimeter data. This is another case study how you can use hydrodynamic modeling. Now so the problem that we try to understand in this particular case study is normally if you understand if you are working on a flood hazard or flood assessment or any hydrological applications where you are interested in the water availability assessment of particular catchment, the the important in situ data that you are mostly interested in is the water level and the discharge. If you have the well distributed water level and the discharge data, so you use that discharge data set to calibrate or the validate your hydrological or hydrodynamic model, or merely by using just the in situ data that you get, you can do the different trend analysis and you can assess the complete water resources in that particular area. But over a period of time you can see that it is very costly to monitor the in situ gauging stations. Even sometimes what happens is that you have complete in situ observations are there. In situ means you have the gauging sites for that particular river, but sometimes at what density you are looking for, maybe you don't get that dense river gauging stations, you don't get, or sometimes even you don't get data at all. Maybe that basin is completely ungauged or it is sparsely gauged. So in that case, people are now working towards how the space observed data, you have abundant amount of space observed data that can be utilized to establish certain virtual gauging network where you can monitor this water level and the discharge. So that is what we try to understand, or that is what we try to aim in this particular case study. So again I will repeat. So here you can see that this is the Tezpur and this is the Guwahati. So these are the two gauging sites that are being monitored by Central Water Commission. India Central Water Commission, CWC, monitors the water level and the discharge for especially almost all the river basins except in the north in Himalayan certain bases, like there is BBMB, Bhakra Bias Management Board, which take care of Bias River, Tirthan River or the Satluj River basins. Now in this case, this is the stage, the start, the Tezpur and the Guwahati. At these two locations I have the stage and the discharge. But what if I want to know the stage and discharge at more densified network? I want to know this additional locations. So here you can see that the black points that you are seeing is basically the altimeter tracks. Now here you can see that this Saral Altica is crossing this river at this particular location and this particular location. At 4 locations you are able to see that this altimeter is crossing this. Now these are basically the virtual stations. Now this Saral Altica is one of the altimeter, or we can say, so altimeter is if you go to the type of remote sensing data, it is basically the non-imaging microwave sensors, which gives you very highly reliable water level values. If you compare those river water level values with the institute data, you will get always guess. Most of the time you will get the accuracy maybe less than the 50 centimeter, 40 centimeter. So you get very reliable water level values using this altimeter data set. Now what if you have the water level at this, and if you could get discharge as well, and if you could generate rating curves at these 4 locations where you have this virtual station. So basically if you could generate rating curves at these 4 locations, so now this 4 location could act as the virtual gauging network. So in addition to the in situ dataset that you have at the Tezpur and Varanasi, at this 4 location could work as your virtual gauging station. That is what we try to address in this particular case study. We generated the rating curves using the hydrodynamic model. So again, this is application of HD model. What we did is we generated the rating curves at this 4 locations, and further we try to evaluate those rating curves, whether the rating curves are generated are correct or not, using the satellite altimetry data. So when we compared the rating curves that we generated to evaluate the generated rating curves, we compared our simulated water level from the HD model and the water level that we got from this altimeter, assuming that water level that we get from the altimeter is very accurate. You can refer a lot of papers where you will find that the efficiency or the reliability of water level that you get from this different multi-mission altimeter data. So now in this case what we found is, for this 352 track of Saral Altica, when we plot scattered plots, we got a good RMS data of around 15 centimeter. NAC was quite good, and there was good match between these 2 time series, which gave us kind of certainty that the rating curve that you generate at this particular gauging station could be very reliable, because this model was already calibrated, validated using the in situ data. Further you evaluated using by comparing simulated water level using the altimeter data. So it is kind of you can say that it is the multi-site validation of your model also. You are not just relying on the in situ discharge data that is there at the outstream end, but basically you are taking help of the altimetry data set that is there to check at different cross section how your model is working. Once you are ensure that at this location if there is a good match between your simulated and the altimeter based water level, you can generate such kind of rating curves, and then these rating curves we can use to find out the discharge value. So these are the water level and the discharge. So for each water level you can find out the discharge value. So this is one of the again application of hydrodynamic modeling that we have tried to show here. Now third application that we have done is the evaluation of topographic based indices for floodplain mapping. Now if you look into this, till now we talk a lot about this hydrodynamic modeling. Now if you look into this hydrodynamic modeling, if you want to run a more hydrodynamic model, you need a different data. So which data set that you require, if I list out, you need a digital elevation model, you need a ground control finds maybe from DGPS and the total station survey, river cross sections, then stream flow data, you need land use land cover, and then modeling surface. So you need this much of information that you require to get this floodplain map. On the left hand side, recently lot of people have come up with this certain topography based indices where they try to give you the preliminary floodplain map, preliminaries, what you can use, you can say those are the static, not the dynamic, but the static floodplain map for a particular river. If you are in an urgent need of certain mitigation planning activities, or you want to go for certain assessment or planning based on the level of hazardness or the flood prone which area is more prone than compared to other for a complete stretch. So you can use such kind of topographic indices. Now you have these three topographic indices like height abound nearest drainage, then TWI is topographic wetness index, and then SP is the slope precision. So these are the three topographic indices. Now the advantage of this topographic indices to delineate the floodplain is that they are very quick. Computational time required is obviously very slow, and the data that you required is only a basically digital elevation model. So this is the only one input required. Ground control points you require to get to separate to give the threshold to differentiate between your floodplain and the upland area. But if you don't have the GCPs, maybe you can get a guess by using the what will be by guessing the certain threshold value based on your experience of that particular study area. If you know that this is the area most of the time gets inundated, if you know the preliminary extent, so you can assume certain threshold also. So you can skip this GCPs. So in that case you only need DM as the requirement to deal in the floodplain. So the idea that came to us that now people are saying that these are working very fine, you gives very good estimate, and it is very quick. This is on the left hand side, and the right hand side we have data extensive hydrodynamic modeling. So in this case what we try to do is we try to evaluate this particular floodplain map that is being generated using the topography indices, and to evaluate this topographic indices we take help of this particular hydrodynamic model, and then we try to see that how there is match between this topography based approach out of three, again which one perform better by which model try to mimic the output that you get from this hydrodynamic model. So this is what we performed. We performed the confusion matrix. So here you can see that's T1, T2, T3. Again basically this is the Manali, then you have this Kullu, and this is the Muntar. You performed, and then we try to came up with the certain statistical parameters that you get from the confusion matrix, and then we came to know that height abound nearest drainage was relatively performing good compared to this other hand and slope position methods where it gives the kappa equation of around 0.6. So in that sense, so this is how that if you don't have any data set, you simply take a DM you already have the add-on of hand. You just give the dm value, and it asks you only for the dm and the river network for which you want to generate the floodplain map, and then you can generate this floodplain maps based on using the hand tool. So this is how in this case study we try to see that which topographic indices relatively tries to mimic better the floodplain map or the reference map that we got using the hydrodynamic model. So this is another application of HD model that we try to address in this case study. Now we come to this the last case study that we have done in this case is the dam release scenario. So now here you can see that this is the Cheruthoni dam. So if you go back to this in the year 2018, so there was a number of spills of extreme rainfall events that led to the opening of multiple gates gates of the different reservoirs that are then in the Kerala river, in the Kerala states. So during that time what we try to do is so we knew that around the gates of this particular Cherudheni dam were open, and the discharge was around 5 gates were open and discharge are around 770 meter cube per second. So what we wanted to see is what is the impact that has happened because of opening of this particular Cherudheni dam, and then what is the impact or which village got affected more, that we try to assess using this particular case study. So what we did is we generated the SD model right from this Cherudheni dam till 17.5 kilometer downstream using the Michelin software, and then we at this particular Cherudheni dam, which was our upstream boundary, we gave this 770 meter cube as a discharge, and we try to see what is the impact on the downstream side. So here you can see that this is so at different locations we try to see the simulated flood. So this is, you can see that this is one of the extent flood extent. Somehow we try to show that in the 3D manner. So so this is how the extent that we got, and then the same after one day or 2 days later we got this particular image that so there is the same the extent, water extent that we try to show was also being actually that area got inundated, and then so it is some kind of preliminary validation of this particular simulated extent that we got. Further, this is the particular bridge, it was inundated, and then same bridge was got heavily damaged during that particular event. So this is how you can you can run that particular model, and then you can see that what is the impact of heavily released flood wave from that particular lake. That also assessment can be done. Now in this case I have shown it for this dam release silo, rather than if it could have been any reservoir, if it is landside dam lake or if it is the glacial lake, the approach will be same. If you know the discharge value, then you just use that value and then you route the model, and then you can see what is the impact on the downstream side. In case of glacial lakes, like glacial lake outburst floods, especially if you are doing, if it is not breached and you want to, so if it breach, what will happen? So in that case what you have to do is for that particular lake you have to use these different satellite images. You have to find out the area of that particular reservoir. If you have the bathymetry survey, then it's perfectly fine. Then using that bathymetry survey you can find out the volume of that particular glacial lake, and then using that volume you can generate the different scenarios, like if that volume gets breached in maybe 2 hours, 4 hours or 6 hours, so what will be the discharge value, and for that discharge values you can see the impact on the downstream side. Again, there are different methods also that how you can generate those different hydrographs, or you can say those synthetic hydrographs from that glacier lake. So that also you can look into it. But if you don't have the bathymetry data, again there are empirical equations where they try to link. There are features or the characteristics of that particular lake with the volume. Like they try to relate your area of that lake with the depth, area of that lake maybe with the velocity, and then you try to approximate certain volume of that lake, and then based on that you generate the hydrographs. And same hydrographs again you try to route using the hydrodynamic modeling. So this is about the fourth case study that again this is the application of hydrodynamic modeling. So this is from my side. Now these are the certain publications that helped us to prepare this presentation, especially I was talking about this satellite altimetry and the HD model. So this is the work you can refer, Advanced Space Research, then Tirthan work, Biasri work. So all these papers that are published work. So if you want to know more about this, you can always look into this paper. You can go to our research profiles. If you have any queries, you can always get back to us. This is my email ID, pdh@iirs.gov.in. So if you have any queries now, so I will take a break of 5 minutes, and then I will get back to you the what are the queries that you have, and we'll try to answer one by one.